Hello and welcome back to Calculus 3. This is exam 2 review because you wanted it, I guess. So the exam is on chapter 15. We have sections 15.1 through 15.8. The last one is the Lagrange, what we covered yesterday. 10 questions. And we'll try to stay away from those that take an hour to solve. Let's say the ones with min-max and Lagrange that could really take a long time. So starting with the graphs and lever curves. Number one, you must know definition of multivariable function verbatim. Goes for everyone. Another skill that you definitely need to know to get the domain of a function. Number 3, level curves. We said those are the cuts. Number 4, limits. And those break into 3 categories. The plug-in one, the boundary, which is the algebra, and two-path limit does not exist. Number 5, partial derivatives. Number 6, chain rule. There are 2 different types of problems you can expect. One is going to be just to draw the tree, which is you have some really complicated function and you just need to draw the tree, write the formula, or something that is smaller tree but compute all the way. So it's either going to be just setup, which is tree plus formula, or smaller tree, do the entire problem. I hope it makes sense. The next one is directional derivatives. I'll put in blood U hat unit vector. Number 8, gradient. Number 9, tangent plane. Nice one. Number 10, linear approximation. Guys, that's a tangent plane. It's the same. Number 11, differentials. Finally, 12, min-max saddle. And number 13, Lagrange. So there are these 13 skills. Lagrange, word problem. So 13 skills in 8 sections in one chapter, where 8 and 9, so it's technically 12, because tangent planes and linear approximation is the same thing. So technically 12. Now, do you really need a problem on partial derivatives on its own? Obviously not, because partial derivatives will be the part of the chain rule, directional derivative, gradient, tangent plane, right? They all have partial derivatives within. There is no need to have a standalone problem, find the partial derivative. With min and max, you have to find the first partial derivative, then you have to find the second partial derivative. So there is really no need to have a standalone partial derivative problem. If you have a definition of a function, multivariable function, it's a 4-point question. That could be maybe problem 11, let's say, I don't know. It's only 4 points. It's not something that you have 10 points as a question. Getting domain of a function. So maybe definition of a function and getting domain and calculating one level curve. That could be a 10-point question if I put all of those as A, B, and C in one problem. So that could be a 10-point question. And then have a question on limit, and then question on chain rule. To clarify one more time the chain rule, we had the problems where the trees were very large, and calculating the full problem would take very long time. You remember that for chain rule, you have to follow all of the branches that start at the function and add with the parameter that you are taking the derivative in respect to. So you can have multiple branches going towards that parameter. You have to add all of those. So depends on how much it fractures, the problem can become extremely long, and then obviously computing and shoveling through algebra to get all of that simplified might take a very long time, which is what we don't have on the exam. So you can either expect a large tree where you just draw the tree and you draw, or I give you the tree, you write the formula, or I give you the functions, you draw the formula and, you draw the tree and formulas. Or you might have a smaller problem where you have functions and you need to calculate everything. So in that case, obviously the tree, you draw the tree and you write the formulas, but they will only have maybe 2 or 3 terms. So that's something that you can take care in 5 minutes. So it's not a big deal. Limits. Limits have the basic limits where you can just plug in the value, you get a value back, and you're done. So that's the easy ones. The boundary problems are the ones where when you can factor and you can rationalize and you can do some of those algebraic manipulations, and stuff usually cancels, and then you're able to plug in and solve the problem. And finally, the 2-path limit does not exist. Well, it doesn't have to be 2-path. You can do y equal mx squared, y equals m root x, and so on. So there are a lot of different ones that you guys can work with. And the idea is to find 2 different functions, which are actually the paths, that go through the point of interest, which is where your xy is going to, I don't know, approach 0, 0, or is it going to approach 1, 1, whatever it approaches. So your function that you are picking has to go through that particular point. And generally, that's the one that doesn't go well. So please pay attention to the non-existence of limits by 2-path or more. Directional derivatives, I already wrote in blood over there that the u hat is a unit vector. In general, you don't have the unit vector, you just have a vector. And then you lose a lot of points because you don't transform that unit vector into, that vector into a unit vector. So you must, as soon as you see, for directional derivatives, as soon as you see that you need to make sure that it's transformed into unit vector. If you don't remember the formula, and you should, vector u hat is equal to what? Vector u divided by
Magnitude of
u. Very good. So that's the way to get the unit vector if you don't have one. So if I give you a vector 1, 2, not a unit vector. You'll write, because the magnitude is root 5. So you guys will have to change that one into a unit vector. Gradient, very simple, right? It's just a vector of partial derivatives, whether it's 2D or 3D. Tangent plane, memorize the formula. You can know explicit only, but also implicit is, implicit only, but you can do explicit as well. Linear approximation, same deal. Differentials, again, a formula. And that takes us to min-max saddle, where you have to know the second derivative test, which is that big D formula with fxx times fyy minus fxy squared. That's the formula that does the test. And then the three rules. If D is smaller than 0, if D is larger than 0, if D is equal to 0. So all of those rules. Lagrange word problem. We did 4 or 5 problems yesterday in class for Lagrange. Now you guys have Friday, Saturday, Sunday, and Monday. Your exam is on Tuesday. So you have 4 days. And if you haven't done the test prep, the sample exam in MyMathLab, it is time to do it today, because you need to know where the holes are, so you have enough time to plug this on, to plug those holes over the weekend, Friday, Saturday, Sunday. So make every effort to complete your sample test. It's called Chapter 15 Post Test in MyMathLab. So you go to assignments, you change it to quizzes and tests, and then just scroll down. So it's not in the same group where your quizzes are. You go further down, and eventually you will find the line which says Chapter 15 Post Test. And you take that exam. Those grades are your own. No one can see those. You just work your stuff through that sample exam and try to do it the same way like you would do it when you are in classroom. So no notes, no formulas. Just test your knowledge so you can plug in whatever is missing. Lagrange multipliers, the word problem. Again, look for symmetry. If you have symmetry in equations, that means that those variables are the same variable, and you guys will be okay. Are there any questions? Any problems to enjoy? Yes? Everything. So for our honors, you guys, well, already definition of the multivariable function like everyone else, obviously, to get the domain curve. So fx and fy derivation. Derivation for directional derivative. And there is no that. So you have these. Great. The network just died. Yep. It's back. Good. False alarm. Any other questions, concerns? Any problems? How about something Lagrange? Word problems? We only did 2 yesterday. We did shipping and we did the ellipse, I think. Yeah. Right? They have a lot of... I love Lagrange. I should put 4 Lagrange problems in the test. We did the shipping regulation, box with minimum surface area. We didn't do minimum distance to a plane. Well, that sounds like fun. Minimum distance to a plane. What's the minimum distance from the tip of your nose to the wall? Because the wall is a plane, right? And your nose is a point in space. So what's the minimum distance between your nose and the wall right there? That's technically what this question is all about, which is awesome. Find the point on the plane, 2x, 3y, 6, right? Closest to the point negative 2, 5, 1. I just feel like doing one of these before I die. So 32, min distance to a plane. So your plane is given as 2x plus 3y plus 6z is equal to 10. And point is negative 2, 5, and 1. So to understand this, we can just sketch a plane in space and a point in space, and then this line, so that the line that connects, so this is the unknown xyz which lives on the plane, this is the known negative 2, 5, 1, this is the plane which is 2x plus 3y plus 6z equals to 10, 2x plus 3y plus 6z, yep. And I mean, we should immediately start dreading this because we see there's no symmetry, right? But such is life. And we want to find the minimum, right? Minimum distance. So now we know that we have to use distance formula because you're looking for the minimum distance between the point and the plane. If you draw it this way, it's going to be longer. If you draw it this way, it's going to be longer. So any other way would be longer than this way. Now the distance in Euclidean space, since on small scale, it always applies, right? We have x minus plus 2 squared plus y minus 5 plus z minus 1 squared, and that would be our distance formula. So, and we need that to be minimum. So we know that our f of x, which is the objective equation, is the distance formula. So x plus 2 squared plus y minus 5 squared plus z minus 1 squared is our objective equation. And we have g of xy, which is g of xy, which is our equation of the plane. That's the constraint. The point has to be on the plane, hence constraint. So that's 2x plus 3y plus 3z minus 10 equal to 0. That's to trigger people. Constraint. And now it's time to do the Lagrange. Del f equals lambda del g. And all we need to do here is partial derivatives. Well, yeah, it's going to be a living nightmare, partial derivatives for f, but not right, still possible. So when you're taking derivative of a square root, it's always 1 over 2 times square root. But if there is a function under the square root, then the derivative of that function goes on top. So the derivative over here would be the entire square root, the same way it is, and then times the derivative of this, but only for x. So it's 2 times x plus 2 to the first power times derivative of 1. So now all I need to do is to repeat this 3 times. So I have it here. I have this denominator. Copy. And paste. So I have this denominator. And I have 2y minus 5 times 1, comma, another one, paste, no one there, the numerator is 2z minus 1, equals to lambda, and now derivatives of g, and those are easy. 2, 3, oh, this is supposed to be a 6. It's 2, 3, 6. 2, 3, 6. So at least we have these ones to be easy. So now that I have the equation here, I write the set of 4 equations, because it's a three-dimensional right input here. We'll have 3 equations, and then the constraint g is the 4th equation, because we also have lambda as a variable. So 2x plus 2 divided by 2 times, oh, just going to cancel all of these 2's. We don't need these 2's. There we go. So it's just x plus 2 divided by, I'm just going to call it a square root. We don't have to write all the whole thing. Is equal to 2 lambda. Y minus 5 divided by the square root is going to equal to 3 lambda. And z minus 1 divided by the square root is going to be equal to 6 lambda. And I have 2x plus 3y plus 6z equal to 10. So this is my system here. That's my system, and I just need to solve it. So we can start by eliminating lambda by multiplying top equation by -3, second equation by -2, and then add each one. That would eliminate all lambdas. So you have -3 times x plus 2 divided by the square root plus z minus, -2, no, z minus 1 has not multiplied because 6 lambda. So z minus 1 over the square root equal to 0. So that's when you combine first and third. Now you combine second and third. So that's going to be -2 y minus 5 divided by square root plus z minus 1, come on, over the square root equals 0. And we still haven't used 2x plus 3y plus 6z equals to 10. We'll get there eventually. So now this is my new system here, pretty much like a new problem. And what I can do now is, I hope, well, first we're going to move these negative terms to the right, and you see that the square roots cancel on both sides. So you can say times the square root and times the square root, and then the square roots are just gone. So the first equation becomes z minus 1 is equal to 3x plus 6, because the negative becomes positive 3 when it goes to the other side of the equation. The next equation is z minus 1 is equal to 2y minus 10. And we still have the 2x plus 3y plus 6z equals to 10. Now guys, you might be tempted to solve for z, right? Because that's what you are trained to do. But please try to look at the forms rather than just, what you trained. I hope you see that this z minus 1 is exactly the same as this z minus 1. So if they are exactly the same, there's no reason to solve for z. You can just set these two equal to each other because their left sides are equal to each other. There's no reason to, right? So that's going to make this into equation. Now, you have the z in the third equation here, and you need to eliminate that z. So you can do that from here, because z is equal to 3x plus 7. And that's going to go into this equation here. So I have now 3x plus 6 is equal to 2y minus 10. That's when I set the two equations equal. And then the bottom equation is 2x plus 3y plus 6 times 3x plus 7 equals to 10. And we are down to two equations, two unknowns. Move everything to the left in terms of variables. So 3x minus 2y is equal to negative 16. And simplify the one on the bottom. We have 2x plus 3y plus 18x. That's plus 42 equals to 10. So is that 20? Yeah, that's 20x. So 20x plus 3y is equal to negative 32. Three doesn't go into 20, so we're gonna abandon x and work on y. So that's going to be top equation times 3, bottom equation times 2. So top equation becomes 9x minus 6y is equal to negative 48. And the bottom equation times 2 is 40x plus 6y is equal to negative 64. When you add the two equations, you get 49x, y's are cancelled, is equal to negative 112. I don't like these numbers, but such is life. X equals negative 112 divided by 49. 49 times 2 is 49 times 3. Yeah, doesn't work. So there could be algebraic mistake somewhere. in the last 15 pages of work. But we have x. And now you can calculate y. And then, so now you get y from 3x minus 2y equals to negative 16. And then get z from the equation of the plane, which was 2x plus 3y plus 6z equals to 10. So you just plug in x into this x here, you solve for y, you get your y, and then you plug in your x and you plug in your y, solve for z, and you have the numbers. Now, the reason why I'm not going through this, it's because probably there's a mistake somewhere up there, or maybe not. Maybe x is negative 112 over 49. I don't know. It's just not worth spending time to go back to calculations. You should redo this problem at home. Write out everything carefully and make sure that I didn't make any mistakes. I just want to make sure that I copied the equation correctly. That's the problem. 32, 2x plus 3y plus 6z equals to 10. Negative 2, negative 2, positive 5, positive 1, which makes it plus 2, minus 5, minus 1. The derivative is 2 square root. The derivative of this is 2x to the 1 times 1. 2 is cancelled. I'm 100% sure that everything is good up to this point. So everything is good up to this point. From this point on, you have the few ways in which you can solve this. So I decided to eliminate lambdas first because, as I said, we try to eliminate lambdas first because lambda is the only value we don't actually care about for our answer. It's just a vehicle for us to get to the answer. The catalyst. Okay? It's still going. Wow. Okay. Any questions, concerns, problems? Yes?
I have a question on number 25 and 15 for me. I'm just confused about how to deal with the whole scenario where x cannot equal 0 and how to get that covered from there.
20 with the x squared plus y plus z?
Yeah.
Okay, let's take a look. It's fun. It's called mathematical gymnastics, right? So we have our function f given as 2x squared plus 2y squared plus z squared equals to 2. 2x squared. Okay. So del f equal lambda del g, and I have f, so it's going to be partial f, so that's 2x, partial y is 1, partial z is 1, equals to lambda, partial x is 2, partial, this g was supposed to say minus 2 equal to 0, oops. So partial is, for g, is 4x, partial for y is 4y, partial for z is 2z. So these are our methods. And now we're going to have the situation that 2x is equal to 4 lambda x. Oh, nice. This is great. 1 equals 4 lambda y, 1 equals 2 lambda z, and we have the g equation. Now look at the first equation, guys. It's amazing. You see that x equals x, right? No other variables. X equals x, that means that this equation here means that 2 equals 4 lambda. Lambda is a half. Thank you for asking this problem. This is not easy to find which problem is going to be the one that just hands you lambda on a plate. Even though you don't care about lambda, hands you lambda, and with lambda you quickly solve all others. Because now you know lambda is a half. That is immediately going to make, if lambda is a half, you can calculate y and z as a joke. You saw me not even write the g equation, because I saw this equation and I immediately knew that I don't need g. Because I have lambda, and because I have lambda, now I plug in lambda over here, and when I plug in lambda over there, I get that y is 1/2, and z is 1. And oh, actually we do need g. Oops, because you need g to find x. Yeah, I got too excited. So now you need to use g equation to calculate x, and g equation was 2x squared plus 2y squared, so that's going to be a half, plus z is 1, still 1, equals to 2, so that's 1/2, so x squared is equal, 2x squared is equal to a half, x squared is equal to a quarter, so x is going to be equal to plus minus half. And we are getting 2 points. There is 1/2, 1/2, and 1, and negative 1/2, 1/2, and 1. So we have 2 points as the answer. We didn't go out of our way to calculate lambda we don't need. It was handed to us on a plate, and we used it to quickly calculate everything else. So some problems can be quickly solved this way. I'm out of water. Think of the next question. I just get to. I'm getting to the point where I don't want to go. Any other questions? Problems? I can go and die in peace. Directional derivatives, everyone good? Gradient times the unit vector. Make sure you have the unit vector there. Memorize definition of a function. The function is a rule which assigns to each point A, B in a domain a unique z in range. Domain is found the same way as in algebra, except now your answers are no longer intervals of numbers, but shaded regions in XY plane. It could be a circle, could be half a plane, could be above the line, below the line. We did a whole bunch of examples there. Make sure you memorize the formula for D, for min-max saddle. Make sure you, along with that, know the rules, how to sort out. So we have larger than 0, and D larger than 0, fxx smaller than 0 is a max. D larger than 0, fxx larger than 0 is a min. D smaller than 0 is a saddle. D equal to 0 is inconclusive. So there are 4 rules that accompany the second derivative test for min-max saddle. Obviously, you know partial derivatives, and I talked about the chain rule. You just take a look at examples, and please, if the problem says compute the derivative at t equals 2 or t equals 10 or whatever, make sure I did say this when I returned the first test, but it's worthwhile saying again. Make sure when you are done with the problem, every time, not just for my test next week, every time you do an exam, you solve a problem. Once the problem is done, go back and read the problem one more time. Is there a part B? Is there an extra question that you did not answer? And so on. Because find a partial derivative and you just check out from reading the rest. The question is find a partial derivative and compute that t equals to 1. So if you don't compute it, t equals to 1, you haven't finished the problem. So you can't score the full points. Make sense? Good. Any other questions, concerns? All right. I'll see you Monday.